Hello and welcome to this video about deriving Simpsons rule. This is a rule that is used to calculate the area under a curve, using a few samples of the height of a curve, and then multiplying these heights by some set constants. This rule tries to approximate the curve using a series of parabolas, which are polynomials of degree 2. And then using these parabolas to calculate the area under the curve. Of course, the parabolas are hidden from view, and the user doesn't need to know what the coefficients of these parabola polynomials are. Now we'll write down the coefficients of this parabola here for one segment, because we'll need to know them while we derive Simpsons rule. Because only 3 points are needed to find the parabola polynomial, then it means that it will retain its shape when shifted to the left or right by any distance, and so the rule can be derived by any 3 values of x equispaced by 1 on the x-axis. So we'll start with values of x equaling 0, 1 and 2. By making the values of x closer together, that is, by using different values of h, this only scales the parabola in the x direction, and its area is equal to multiplying it by h. So using these values of the parabola of 0, y0, 1, y1, and 2, y2 should give us Simpsons rule. So I'll set out this problem again so as to make it easier to follow. This system of equations may be rewritten as this matrix equation, as written here. So now to evaluate the values of this matrix. And now to find the values of a, the coefficients of the parabola polynomial, in terms of y, the heights of this polynomial. And evaluating the inverse of this matrix gives us this new matrix. And now to evaluate the shaded area under the curve using calculus. The antiderivative of this polynomial may be easily found, and so we write the next step of this equation. And now to substitute the values of 2 and 0 in for x. The part of this equation corresponding to x is equal to 0 is obviously equal to 0. So we'll just evaluate and write down the part of this equation corresponding to x is equal to 2, which gives us this value of the area in terms of the coefficients of the polynomial. This may be written again as this matrix equation. So now we have these two matrix equations which we'll use to find Simpsons rule. If we substitute equation 1 into 2, we can get the area in terms of the heights, and without knowing the coefficients of this parabolic polynomial. And so this row vector and matrix multiply together to give us this row vector, which is Simpsons rule for 3 points. When more points are used, the points may overlap, so the thirds add together to make 2/3. And so just to illustrate how some of these points overlap, we'll look at this arbitrary function here, which uses a series of parabolas to approximate it. So this is the area under the curve which is approximated by these parabolas, and called Simpsons rule. Notice that for the calculation of each different Simpsons region, some of these heights are found twice in the calculations, like for example y0 and y4. Since these occur twice, they are added together, and the coefficient used is 2/3, because the 2 1/3 are added together. We may also derive Simpsons rule from x is equal to -1, 0 and 1, because it doesn't vary if it is derived from any 3 equispaced points. So these equations may be written as this matrix equation. And so we'll evaluate the values of this matrix and get the polynomial coefficients in terms of the heights, and then evaluate the inverse of this matrix to give us this new matrix. Finding the inverses of matrices is easily done by computer. And now to find the shaded area under the curve using this integral. And this is the next step, since the antiderivative is easily found for a polynomial. And so we substitute 1 and minus 1 in for x. And then we evaluate each part of the equation. And evaluating this integral gives us this equation. And it may be rewritten as this matrix equation. And so we end up with these two matrix equations. Substituting 1 into 2 gives us this matrix equation, which gives us the area without the use of any of the polynomial's coefficients, and only the heights of the function. And simplifying this equation gives us this equation, which is equal to Simpsons rule for this single Simpsons region. We can find Simpsons rule for any 3 points that are 1 unit apart more generally. These equations may be rewritten as this matrix equation. Notice that the existence of variables as elements of this matrix make it harder to solve. It's better to solve it using numbers. Expanding out the expressions gives us this equation. And the vector containing the values of the coefficients may be found in terms of the vector containing the heights. And the inverse of this matrix may be found. I've written a computer program to do it for one variable, and I've tested it for about 20 different values of n. I might show you how I've done it in a different video, if anyone has any interest in seeing it. And so now to find the shaded area under this curve for these same 3 points using this integral. And we can write it out like this after we've found the antiderivative. And substituting the numbers in gives us this, which looks like it could become very messy. And expanding out this expression gives us this, which gives us this expression in its most simplified form. And this expression can be rewritten as this vector equation. And so these two past calculations give us these two matrix equations. And substituting the first equation into the second gives us this equation. So the area can be found only using the heights and not needing the coefficients. And simplifying this equation gives us this equation, which is Simpsons rule. And now to look at how to derive it more generally. We have to use the points and equations listed here, and h can become as small as we desire, but not infinitesimally small. And we have this complicated matrix, which we have to find the inverse of. And then we have to find the area under the curve using this integral. And so this is the next step in the calculation, using the antiderivative of this polynomial. And then we substitute all of the values in for x. And then we expand and simplify this polynomial expression. And so we can rewrite this expression as this vector equation. And so we have these two matrix equations, which we must solve to find the area only in terms of the heights y0, y1 and y2, and without knowing the parabola coefficients a0, a1 and a2. And after substituting 1 into 2, we get this equation, which after simplification gives us Simpsons rule for one Simpsons segment. This is a rather long way to solve it, and the previous methods seem to be easier. And now to find Simpsons rule by sampling. We know that it is going to be linear, and there are 3 coefficients to find. So we need 3 groups of data so as to find the square matrix that we can invert and thus use to find them. We can use any parabolic equations and any 3 values for x 1 unit apart, like 0, 1 and 2. But we've got to use these 3 values of x in all 3 groups of data once we've chosen them. So we'll first use this parabolic equation here. And so we'll find the values for y by substituting these values of x into this polynomial. And now to find the area under the curve for this shaded segment using this integral. And so this is the next step in this calculation using the antiderivative. And this is what it is after substituting in the values for x. And so this is the answer, the area of the segment as a number. And this is how we can write it out as a vector equation. The values of b will equal the coefficients of Simpson's rule for one segment. And so we can gather information from the next parabolic equation. These are the values of y. And now to find the area of this segment from this integral. And this is what this integral is equal to. And so we can write out this vector equation, which we'll use later to find the values of b. And so this is the third parabolic equation, giving us the third sample of data. Here are the third samples of y. And here is the third sample of area being equal to this integral. And this is the value of this integral, and is equal to the area of this segment. And so we get this third vector equation being used to find the values of b, being the Simpsons rule coefficients. And so collecting all these 3 sets of data together gives us these 3 equations. We can pack them all up together into this one equation. It will give us a solution for b, so that these values of b will be true for all of the 3 data sets given above, and will therefore solve these 3 equations, and give us the Simpsons coefficients. And so, if you're familiar with matrix algebra, then we can solve this matrix equation to give us this unique solution for b, which is equal to the coefficients of Simpsons rule. You can use these methods to find coefficients for many other types of numerical integration, like for example Simpsons 3/8 rule or even the trapezoidal rule. And now to find coefficients to calculate the area under the shaded segment as shown. We can find the interpolation matrix like we did before, which we need for this derivation. And now to find the area in this segment from this integral. And the first step is to find the antiderivative. And the next step is to substitute values in for x. And then to evaluate the powers of 1. And then to simplify this expression. And this expression can be written as this vector equation. And so then we have to find the coefficients from these 2 equations. And substituting 1 into 2 gives us this equation. And simplifying this expression gives us this equation. I've tested it a lot to check that it works. The main thing is that you can understand the methods used to derive them and use them to find coefficients for other rules like Simpson's 3/8 rule or the trapezoidal rule. You could even be creative and use other functions like log, cosine, or the exponential curves that you could put in the mix so as to make new numerical integration schemes. So I hope that this video has been helpful for you, and I wish you good luck in your quest to make new custom and tailor-made numerical integration schemes that are much more helpful and useful for your special tasks that you need them for.